Dear 4th grade students at the Department of Economics, welcome to our 5th recorded lecture for the Econometrics module. I very much hope that you are all in the best of your states. Kindly note that the recorded lecture is to be used in conjunction with your textbook. In the current presentation, we extend the two-variable regression analysis to multiple regression analysis, in which we have more than one regressor. In other words, we have two regressors or more, say a k number of regressors. Why do we extend the two-variable regression model to multiple regression analysis? Well, in practice, the two-variable model explained in the previous chapters and previous lectures is often inadequate. For instance, in our consumption income example, we assumed that income is the only regressor that affects consumption. However, economic theory is not so simple. In addition to income, a number of other regressors are also likely to influence consumption expenditure. An important variable is wealth of the consumer. As another example, the demand for a product is likely to be affected by not only its own price, but also by the prices of other substitutes or complementary goods, income of the consumer, and social status. Hence, we need to extend our simple two-variable regression model to cover models involving more than two variables. In other words, we need to discuss the multiple regression models in which the dependent variable depends on two or k regressors. The current presentation explains the k-variable regression model in which there are a k number of regressors. Then, we resume the OLS method in the context of multiple regression analysis. Other points covered include the polynomial regression models. Furthermore, we will consider some numerical examples in the current lecture for illustration. Chapter 7 of Gujarati 2004 starts with the three-variable model in which there is one dependent variable and two explanatory variables. This three-variable model can be generalized to a k-variable model in which there are k number of regressors. We can show the population regression function of the k-variable model by equation 1. In this equation, y is the dependent variable, x's are the explanatory variables. Finally, u is the stochastic disturbance term. Equation 1 consists of two components. The first component is the deterministic component. It is the conditional mean of y. The deterministic component is highlighted using yellow color. The second component is an unsystematic or random component that is highlighted using the green color. Beta 1 is the intercept term. As before, it gives the mean or average effect on y of all the variables excluded from the model. Although its mathematical interpretation is the average value of y when x2, x3, and all other explanatory variables are set equal to 0. The coefficients beta 2, beta 3 until beta k are called the partial regression coefficients. They measure the effect of the corresponding variable when the other variables are held constant. For example, beta 2 measures the change in the mean value of y per unit change in x2, holding the other variables constant. Later in the current lecture, we will consider numerical examples in which we regress the dependent variable in more than one regressor. In order to estimate the parameters of the k-variable regression model shown by equation 1, we adopt the method of ordinary least squares introduced in chapter 3. As you already know from chapter 3, the population regression function shown by equation 1 is not directly observable. It is estimated from the sample regression function that is shown by equations 2 and 3. Note that beta 1 hat is the estimated coefficient of beta 1, beta 2 hat is the estimated coefficient beta 2, etc. Ui hat is the residual term, that is the sample counterpart of the stochastic disturbance term. In order to determine the sample regression function shown in 2 and 3, we can express equation 3 as shown in equation 4, which we have already done in chapter 3 for the two-variable regression model. As noted in chapter 3, the OLS procedure depends on choosing the values of the unknown parameters that make the residual sum of squares as small as possible, as shown by equation 5. The actual minimization of the residual sum squares in equation 5 involves calculus techniques. We take the partial derivative of the residual sum squares with respect to each estimated coefficient. This is followed by equating the resulting equations to 0. Hence, we can solve them simultaneously as we have done for the two-variable model. However, the expressions for beta 2, beta 3 up to beta k are very complicated and require using matrix algebra. Standard computer programs such as eViews and Stata can carry out all the calculations and provide estimates immediately. Our objective in regression analysis is to draw inferences about the population regression function on the basis of the sample regression function. Given that we don't observe the population regression function, we only guess what it might be. This is important because our ultimate objective is to find out what the true values of the betas may be. Thus, we need a bit more theory, which is provided by the classical linear regression model, which we have discussed before in previous lectures. Now, let's resume the assumptions of the classical linear regression model we have studied in previous chapters and lectures. We continue to work within the framework of the classical linear regression model, which is introduced in chapter 3. These assumptions are valid for the three-variable regression model and k-variable regression model. The first assumption is that the dependent variable can be computed as a linear function of a specific set of independent variables plus a disturbance term. The second assumption is that values of all regressors are non-stochastic and fixed in the repeated sampling. As mentioned in the previous lectures, by this assumption we mean first that x is a variable whose values are not determined by some chance mechanism, but these values are determined by the investigator or the researcher. Second, that is possible to repeat the sample with the same independent variable values. According to the third assumption, the expected value of the disturbance term is 0. Assumption 4 requires that all disturbance terms have the same variance, thus they are homoscedastic. Assumption 5 highlights the serial independence of disturbance terms. In other words, it requires that all disturbance terms are independently distributed or more easily are not correlated with one another. This assumption has a special significance in economics when time series datasets are employed. This assumption means that the disturbance in one period shouldn't be related to a disturbance term in the next or the previous period. Let's consider an example to explain this assumption. Assume that you have weekly data of a given variable, say x. Hence, this condition means that the disturbance term of week 7, for example, is not related to the disturbance term of week 6 or week 8. This condition is frequently violated. This is because if there is a disturbing effect at one time, it is likely to be persistent. It's likely to persist. Violation of this assumption is the topic discussed in chapter 12. According to assumption 6, the covariance between the error term and the regressors must be 0. For the seventh assumption, the number of observations must be greater than the number of parameters to be estimated. Assumption 8 states that each regressor must have some variability. By this assumption, we mean that not all observations of a regressor are the same. Assumption 9 emphasizes that there is no specification bias or specification error in the model used in the empirical analysis. Regarding assumption 10, it states that there are no exact linear relationship among the explanatory variables. As mentioned in previous chapters and previous lectures, based upon these assumptions, the ordinary least squares method provides the estimators of the parameters of the population regression function that have some desirable statistical properties. That these estimators are best linear unbiased estimators. Recall from chapter 3 and from previous lectures that the OLS estimators for the regression coefficients are random variables, since their values will vary from sample to another. For this reason, we need a measure of their variability. This measure, as you already know, is the standard error. Remember that we need the standard errors to establish confidence intervals and to test statistical hypotheses. Given the assumptions of the classical linear regression model, we can easily derive the variances and the standard errors of the coefficients. However, we will not present the actual formulas to compute them, since statistical packages such as eViews and Stata produce them easily as you already know from the current course and from the course of computer applications in management and economics, which you studied in the previous year. Recall from chapter 3 that the coefficient of determination is the measure of the goodness of fit of the regression line. For the multiple regression, the multiple coefficient of determination, which is denoted by an uppercase R squared, is the measure of goodness of fit of the regression line. Again, it is measured by dividing the explained sum squares by the total sum squares as shown below. The multiple coefficient of determination gives the proportion of the total variation in the dependent variable, which is explained by the regressors. As before, its values ranges between 0, that means no fit, and 1 at most, which means a perfect fit of the regression to the data points. One disadvantage of the multiple coefficient of determination is that it is an increasing function of the number of regressors. That is, if we add a variable to the model, the multiple coefficient of determination values increase. Why is this the case? To answer this question, let's compare the coefficient of determination for the k-variable regression and for the two-variable regression model that we studied in chapter 3. We compare the numerator and the denominator of each formula. Note that the numerator in each formula is highlighted in yellow, whereas the denominator is highlighted in green. It's quite easy to recognize that when additional explanatory variables, I mean x's, are included, the numerator increases, whereas the denominator is still the same. Thus, the proportion of variation on y explained by the x's will always be increased regardless of the importance or not of the additional regressor. For this reason, the multiple coefficient of determination cannot be used as means of comparing two different regression models containing different numbers of explanatory variables. For such a case, we require a different measure that takes into account the number of explanatory variables included in each model. This measure is called the adjusted R-square because it is adjusted for the number of regressors by adjusting for the degrees of freedom. Note that the adjusted R-square is often used to compare two or more regression models that have the same dependent variable and the same number of observations. Now, let's consider some numerical examples for multiple regression models. The first numerical example to be considered is the child mortality example. In chapter 6, we studied the relationship between the child mortality and per capita gross national product, and we found that per capita GNP has a negative impact on child mortality, as one would expect. Now let's consider the effect of the female literacy on child mortality. Theoretically, we expected that the female literacy too will have a negative impact on child mortality. Now, when we introduce both variables in our model, we need to net out the influence of each of the regressors. That is, we need to estimate the partial regression coefficients of each regressor. Thus, our model is shown by equation 7.6.1. Using the data given in table 6.4 and employing the method of ordinary least squares, we obtain the regression shown by equation 7.6.2. Let's interpret these regression coefficients. Regarding the partial regression coefficient of the per capita gross national product, we could say that on average, as per capita GNP rises by $1,000, the number of deaths of children under the age of 5 decreases by around 5.6 per thousand live births, holding the female literacy constant. The coefficient of the female literacy tells us that holding the influence of the per capita gross national product constant, on average the number of deaths of children under the age of 5 declines by about 2.3 per thousand live births, as the female literacy rate increases by 1%. The intercept coefficient could be interpreted as follows. If the two regressors were set at 0, child mortality will be quite high. It would be around 263, which makes practical sense. The multiple coefficient of determination value of about 0.71 tells us that around 71% of the variation in child mortality is explained by the per capita gross national product and the female literacy rate. The coefficient of the multiple coefficient of determination is fairly high value, considering that the maximum value of it can be at most 1. Note that the value of the multiple coefficient of determination is lower than its corresponding adjusted R-square, because the latter adjusts for the degrees of freedom. Let's consider our second numerical example for the multiple regression model. Recall that in chapter 6 and in the previous lecture, we used the double logarithm transformation to convert the nonlinear relationship of the Cobb-Douglas production function into a linear regression, so that we can work within the framework of the classical linear regression model. The Cobb-Douglas production function in its stochastic form may be expressed by equation 7.9.1, where y is the output, x2 is the labor input, x3 is capital input, u is the stochastic disturbance term, finally e is the pace of natural logarithm. By taking the natural logarithm of both sides of equation 7.9.1, we obtain the linear model that is shown by equation 7.9.2. This model is linear in parameters beta dot, beta 2, and beta 3, and therefore it is a linear regression model. Kindly remember that beta 2 is the partial elasticity of output with respect to the labor input holding the capital input constant. Likewise, beta 3 is the partial elasticity of output with respect to the capital input, holding the labor input constant. The sum of beta 3 and beta 2 gives the information about the returns to scale, as we mentioned in the previous lecture, and as you already knew from the mathematical economics course. Using data shown in table 7.3 for the agriculture sector of Taiwan for the period 1958 to 1972, the OLS method is used to estimate the production function of this sector, shown by the model in equation 7.9.2. Empirical results are shown by equation 7.9.4. From equation 7.9.4, we could say that over the period under consideration, holding the capital input constant, a 1% rise in the labor input resulted in the average to around a 1.5% increase in the output. Similarly, holding the labor input constant, a 1% increase in the capital input led on the average to about 0.5% increase in the output. Thus, by adding the two output elasticities, we could say that the Taiwanese agriculture sector was characterized by increasing returns to scale over the aforementioned period. The R-square value means that around 89% of the variation in the log of output is explained by the logs of labor and capital. In the next lecture, we will see how the estimated standard errors can be used to test a hypothesis about the true values of the parameters of the Cobb-Douglas production function for the Taiwanese economy. We now consider a class of multiple regression models, the polynomial regression models that we studied in the previous semester in the mathematical economics course. As you already knew from the mathematical economics course, this class of models is related to functions of production costs. Remember that the relationship between the short-run marginal cost of production of a commodity to the level of its output is nonlinear. It has a U-shape as shown by figure 7.1. If we would like to quantify this relationship from the given scatter points, how would we go about it? In other words, what type of econometric models would be able to capture first the declining and then increasing nature of marginal cost? You already know that such a nonlinear relationship is represented by the quadratic model that is shown by equation 7.10.1. This equation is called a second-degree polynomial, in which the highest power of the variable x represented the degree of the polynomial. For instance, if x raised to the power of 3 is added to this function, it would be a third-degree polynomial, and so on. The stochastic version of equation 7.10.1 is shown by equation 7.10.2. Equation 7.10.2 is termed as a second-degree polynomial regression, as we mentioned earlier. For the k-degree polynomial regression, we may introduce it as shown by equation 7.10.3. Note that in these types of polynomial regressions, there is only one explanatory variable on the right-hand side. However, this explanatory variable appears with different powers, thus making them multiple regression models. It is worth mentioning that if x is assumed to be fixed or non-stochastic, then the powered terms of x also become fixed or non-stochastic. Now let's raise some questions. The first question is, do these models present any special estimation problems? Since the second degree polynomial in equation 7.10.2 or the k-degree polynomial shown by equation 7.10.3 is linear in the parameters, they can be estimated by the usual OLS method. The second question to be raised is, what about the collinearity problem? Aren't the different x's highly correlated since they are all powers of x? Let me answer this question. Of course, they are correlated as they are all powers of x, but remember that these terms like x squared, x raised to the power of 3, etc. are all nonlinear functions of x, and hence, strictly speaking, they don't violate the no multicollinearity assumption of the classical linear regression model. Let's consider the numerical example 7.4 that is concerned with estimating the total cost function of a commodity in the short run using data provided in table 7.4. To decide what type of regression models will fit such a dataset, draw a scattergram in which output is represented by the horizontal axis, whereas the cost is represented by the vertical axis, as shown in figure 7.2. As you already know from the microeconomics course and the mathematical economics course, the relationship between total cost and output resembles the elongated S-curve. Note how the total cost curve first increases gradually and then rapidly as predicted by the law of diminishing returns. This S-shape of the total cost curve can be captured by the third degree polynomial shown by equation 7.10.4. Recall that the economic theory imposes some restrictions on the short-run cubic cost function in 7.10.4. These restrictions, as you already know from the mathematical economics course, are shown by 7.10.5. It is important to bear these restrictions in mind when examining the empirical results to determine whether these results agree with the theoretical expectations or not. By applying the method of least squares to the data given in table 7.4, we obtain the estimates of the parameters of the third polynomial regression. as shown below. The statistical significance of the results of equation 7.10.6 will be examined in the next chapter. However, it's your task now to verify that these results agree with the theoretical expectations listed in 7.10.5. An additional task for you is to interpret the regression coefficients along with the multiple coefficient of determination. Now, let's summarize the main points of the current lecture. This lecture extended the two-variable linear regression model to k-variable regression model, in which there are k explanatory variables. We interpreted the meaning of the partial regression coefficients. A partial regression coefficient measures the effect of the corresponding variable when the other variables are held constant. The multiple coefficient of determination measures the goodness of fit of the estimated model to the data under consideration. Values of the multiple coefficient of determination range between 0 and 1, where 0 represents no fit and 1 represents perfect fit to the data points. As for the two-variable linear regression model, the multiple coefficient of determination is obtained through dividing the explained sum of squares by the total sum of squares. Thus, a disadvantage of the multiple coefficient of determination is that it is an increasing function of the number of regressors. To avoid this shortcoming, the adjusted R-squared is introduced. Adjusted R-squared adjusts for the increasing number of regressors through the penalty of degrees of freedom. Adjusted R-squared is often used to compare different regression models that have the same dependent variable and the same number of observations. Furthermore, we discussed the polynomial regression models as examples for multiple regression models. In polynomial regression models, there is only one regressor in the right-hand side, but this regressor appears with different powers, hence making them multiple regression models. Examples of the polynomial regression models include the short-run cost functions of producing a commodity. These cost functions include the total cost function and the marginal cost function of producing a product. These polynomial regression models can be estimated using the ordinary least squares, since they are linear in parameters. Moreover, they don't violate the assumption number 10 of the classical linear regression model. In other words, there are no exact linear relationships among the explanatory variables. This is the end of our lecture. Thank you.